Okay, so now we get to an area in this last part of calculus dealing with Taylor polynomials that gets a bad rap for being difficult to understand and very frustrating. And so it is a little weird, but what I found is that on the AP exam, they tend to ask questions that aren't too crazy based on this. It often appears on the test. In fact, I would say almost always appears on the test. But it's not too crazy. It's just a little weird to wrap our mind around. So here we go. Last class we used, or last video we used a Taylor polynomial where we were able to have an original curve and then come up with, maybe centered at 0, a new curve that at least gets us, some of the values right. And so we get really concerned about, well, how accurate are we close to that center? Like, if my center is 0 and I want to estimate x equals 0.1, how close is that green and that pink line there? How far away am I? And so while we can't actually find the exact value maybe, because if we could, then why would we need to approximate it? What we can do is we can know for sure how close we are. Like we can find the error, or actually we can't find the exact error, but we can find the bounds or the range that our error is in of how close we'll have to be. This really is very similar to AP 1010 whenever we did an alternating series error bound. And we knew that if we took the next term of the alternating series that we didn't use to evaluate, then that term had to be greater than or equal to our error. So we knew that we had to be at least that close. Well, we're going to use the same idea today with Taylor series. So for instance, if I have a Taylor polynomial second degree, and I'll do third degree, which is kind of what I have here in green, then I can use the fourth degree of that to calculate what the most my error might be. And so let's work through this small set of what you must know and try to get this figured out. So the remainder, or the error, reveals the accuracy of our Taylor polynomial, right? How accurate would it be at a set of number of terms of n? So we're always evaluating, a certain number of degrees for our Taylor polynomial. And so the remainder will be the actual function minus our polynomial's estimation. And the absolute value. We don't care about negative. So this reads the absolute value of the remainder of n terms. That should say of nth degree. When we approximate the function at x is equal to the absolute value of the function's actual value at x minus the Taylor's polynomial approximation at x. Well, okay, actually calculating the remainder is only useful if you know the original function's true value at x. And that's not always possible. I mean, if it were possible, then why would we need to have a Taylor approximation to begin with if we could just calculate it? And really, this harkens back to a few hundred years ago, and this is really one of the things that led to the development of calculus, is trying to figure out how to accurately, and in some cases exactly, give values for some pretty weird looking functions. And that's where this whole method of Taylor's polynomial and then figuring out the error all came about. So since, without a calculator, or maybe in other cases, we can't find the real remainder because we don't know the real value of the real function, we want to create some bounds, right? We want to create, well, what's the most our remainder could be? This is the same thing we did with alternating series. Like, what's the most our remainder could be? So the Lagrange error bound, and that's a term you'll see on the test, calculates the error when you don't know the function's actual value. It's very similar to the alternating series error bound. And there's a lot going on here, but really just get the gist of it. This is a general term, that this highlighted orange circling right now is just a general term for Taylor polynomial. at the next 1 degree higher than wherever you stop. Right? Alternating series bound, we use the first neglected term. Well, that's all we're doing here. We are calculating the remainder is going to be equal to the next term. Okay, so number 4, we use the Lagrange error bound to create bounds with which we can find a range of errors. And specifically, those bounds, like the lower possibility and the upper possibility, are called Taylor's inequality. Excuse me. So Lagrange error bound, Taylor's inequality, just the same idea. We're going to use the same equation to find how far away our approximated answer, at however many terms we've been asked to approximate, is or could be from the real answer. When I say could be, we're going to find an upper bound, like this is the farthest our approximation could be from the real value. So we're not quite getting to the real value, but we're finding out the farthest away we could be from it. Now, the trickiest thing will be, what does this max of f to the n plus 1 of z mean? And we'll attack that here in just a second. Let's read through these notes here. Letter A. To calculate the remainder, you'll be given a center. So you'll be given a c, a number that you're centering around, or you're told it's Maclaurin, and that would be 0. You're given an x, so they're wanting you to approximate to this number, or like at x equals 0.1 or 0.2 or 1.3. And you'll be given a number of terms to use to approximate. So you'll be told, like we're going to go, to the 4th degree. We're going to approximate using the 4th degree Taylor polynomial, which means 5 terms. So the n would be 4 for 4th degree, and then the n plus 1 would be the 5th degree. So that brings us to letter B. N plus 1, that means the next polynomial term after how many terms you approximated. And actually, I'm going to change this in your writing. It's the next derivative is what it should read. The next derivative after the derivative you approximated. So it's just like we saw. Okay, think about the alternating series error bound test. The n plus 1 was the next term. Well, here it's not the next term. It still technically means the next term. However, remember, n doesn't represent the number of terms necessarily. It represents the degree of the term. Reading on, so that means that your error will look at the next derivative, f of n plus to the n plus 1 power, and the next degree, x to the c to the nth power, and the next factorial. Okay, so that's not really the hard part. Here's the hard part. This whole idea, max of f to the n plus 1 of z. Okay, first of all, max is a weird word. What's that mean? We know it means maximum, but what does that mean in the application of this? And then what does z mean? We don't even have a z anywhere. X, c, n, but z all of a sudden comes up. So what in the world? All right, so here we go. And this is sometimes the hardest thing to understand. In the terms of AP Calculus, it's just not used in a terribly crazy way. So let's talk about it. Z is supposed to represent any number in the domain between x and c, right? So c is our center, and x is the number that we're going to approximate. And so z is just some number in between there. Okay, well, usually that's not a very big range. Usually we're trying to approximate really close to the center, maybe a 10th off or even a 100th off or something like that. But still, z represents something in there. So reading on, so we calculate the next derivative, right? F to the n plus 1 at that number. So we got to figure out, we'll talk about how do we figure out what z is, but just understand it's some number between x and c. And according to our formula up here at the top of the screen, we're going to find the next derivative at that number. So what's max mean? Well, reading on. Furthermore, max means that we want the biggest possible derivative value that comes out from that number z. So max doesn't mean we want the biggest z, because that would just be the bigger of x or c. But we want the biggest answer that comes out when we plug z in to that derivative. Now you're like, well, how do I know what the biggest answer is going to come out whenever I plug z into that derivative? And that can get really tricky. And so let's look at some practical ideas here, starting with number 2. For z, we will evaluate c in the next derivative and x in the next derivative and use the maximum value of the two. That's 99% of the time. That's the easiest, clearest, and going to give you the winner. So you plug in your x, the number you're approximating at, into the next derivative. You plug in your c, the number you're centering at. And a lot of times, the biggest next derivative of the range between x and c will be the answer of one of those two at that derivative. Not every time. Letter number 3 here, if we have a graph, or if we can use our calculator, we might be able to find the maximum derivative value on the graph between x and c. So like if there's a graph, let's say that we're told to do a 4th degree Taylor polynomial approximation. So that means we want to look at the 5th degree for the max, and let's say our center is here at 1, and we're approximating at 1.1 right here. Well, so if they give us a graph of the 5th degree, maybe that graph looks something like this. And then we see right there where that, where the first or the next derivative is equal to 0. That'll be our max. So we could use a calculator to find out what value here makes that max. So that could be the case if you have a graph or a calculator, that you might actually be able to find it somehow. Now, those are the two general ideas. So you might be given a graph and can use a calculator, and you can find the maximum of that derivative between c and x, or you just, going back up to number 2 here, evaluate c in the next derivative, evaluate x in the next derivative, and use the biggest of those two answers. Now there are a couple of exceptions to the rule, and this gets really kind of tricky. Might really be beyond what you hopefully would encounter on an AP test. But if you're evaluating e to the z and x and c are 0 and 1, then you're going to plug in the highest number 1 for z, and you get what the value of e is, 2.7, etc. And a lot of times you'll just see in calculus, we just call that max value 3. I don't know why, it's just the safest, it's kind of a normal thing. Another normal thing is if you're evaluating sine or cosine of z. We know the outputs of sine and cosine can be any value between -1 and 1, unless it's shifted or something like that. But the period, it's taller. The usual is just to go ahead and select 1 and not even worry so much about the domain. Maybe you're not in a place of sine that could give you 1. But the usual sine and cosine is just to go ahead and let your max of z, the max of the next derivative of z, just be 1. So this can get really tricky. You can rest assured on the AP exam, they're not really going to try to trick you much with it. They do want you to understand that max f to the n plus 1 power of z means z's some number between x and c, and we want the next derivative of it, and we want the biggest possible output. So it might be down here, it might be a visual thing, or you might need to plug in, like here on number 2, evaluate c and x in the next derivative. Those are the main ideas. If you ever see sine or cosine, automatically use 1. This number 4 is a pretty specific scenario, but if you ever have e to the z and your center and your approximated x are between 0 and 1, then just use 3 as the output. And this is true right here. It can feel like a big mess. And so it's something you want to practice. You don't want to lose a lot of sleep over it. But there's a good chance there'll be one question on an AP exam that uses this. And, you can always do extra research, play around with some of the questions on Khan Academy, and do some other things for extra help. All right, finally, one more thing. Maybe not often, but sometimes we'll be asked to find the degree that makes the error less than a given decimal. So in this case, you want to evaluate the Taylor polynomial terms until you find a term that's smaller than your given error. Then your answer is the n before you got to that smaller term. I'm not going to show you an example of this, but the idea is that maybe they want your error to be less than 1/1000th, and so you can find T1, the first Taylor polynomial, then you can add to it T2, then add to it T3, until your Taylor polynomial ends up being a number less than 1,000. And then that means your error is less than 1,000 because that's the next term. And so then you would just say, okay, well, the third term, which is a second degree Taylor polynomial, got us that answer. All right, so let's look at just one really kind of quick example of this. There are different ways that you can encounter this scenario. Let me just give you one right here. And I've seen this on an AP test. Let's say they tell you that the fourth derivative of x is less than or equal to 20. And they say you're going to approximate a Taylor polynomial centered at 0. And they could call it Lagrange instead, but I think a lot of times you'll see it called a Taylor polynomial centered at 0. And you're going to approximate at 0.1. So that's our x. So here we have a c, we have an x. And this whole thing here, and I guess I should say one more thing. We're going to approximate it to the third degree. Or it could say 4 terms. And so whenever you read either of those, then that means that this is the next term, right? The derivative of the next term. And so I've seen this before on the tests where giving you all this information simply means they're telling you that the next term has to be less than 20. So that's our max. Our max is 20. So then if we were going to come up with the value for this, we're going to use that formula at the top. The max of the next derivative is z, so that 20 is going to go all in there. 4 plus 1 factorial, x minus c to the 5 factorial. So here we go. So that number 20, so actually not 5 factorial, it's 4 factorial because we went third degree, so n plus 1 was 4. That's why we had this total. So this is the max in the next term. And then x minus c, 0.1 minus 0 to the 4th term. So I said it wrong earlier whenever I said the 5th. And then you could calculate that out, or maybe that's good enough. All right, so an interesting topic, a weird topic, sometimes a frustrating topic, but there you go. That's AP